So here we go. We are live. So logarithms 4, 6. So what we want to do today, more than anything, is we're going to take a look at some good real world problems that use log.
I don't know, be real world anymore.
Anyway, you are live, so let's go ahead and do this. So first of all, example 1. So a bacteria colony doubles. Big key word. Doubles every 3 hours, okay? Initially, there are 1,000 bacteria. Okay, so find an equation. So if it doubles, we actually have a doubling formula, right? So we have a doubling formula, so this is probably the one I want to use. So my doubling formula is this n of t equals n0 times 2 to the t over a. All right? Now, if it's going to double every 3 hours, that's my cycle of time. That's going to be my little a. So I'm going to put my 3 there. Initially, there's 1,000. That's my beginning amount. That's my n0. Sorry, that looks so bad. So let's set it up. So I'm going to go ahead and put it down. I'm going to go n of t is going to equal my initial amount, which is 1,000 times 2 to the t over 3. All right. So what this is going to allow us to do is find out how many we're going to have left after so many hours, okay? So we just have to plug in the hours and we can find out it's going to double, so it's going to increase, right? As it doubles, it's going to grow. So then B, it says how many bacteria in the colony after 15 hours. So I can put 15 in, and after 15 hours I can find out exactly what the population is. So we're going to go n of 15, or the number of bacteria over 15 hours is going to equal our 1,000 2 to the 15 over 3, all right? And just use our calculator. So I'll probably change that to 5 just to make it easier to put in. So let's see, I'm going to go my 1,000 times 2 to the power of, let's make it 5, right, 5. And so I end up with exactly 32,000. So I get 32,000 bacteria. Okay, not hard, as long as you just use the right formula, okay? Now, C, when will the colony reach 100,000? So what I have to do is this. That's the ending amount. That's going to go in for n of t, all right? So what time will give me an answer of 100,000? So I'm going to set it up as a 100,000 equals 1,000 times 2 to the t over 3, all right? Now, I need to solve for t, and since t is in the exponent, I'm going to have to take a log eventually, right? So before I take a log, though, let's divide by 1,000. So if you divide by 1,000, right? 1, 2, 3 zeros, 1, 2, 3. I get 100 equals 2 to the t over 3, right? And you can just use your calculator if you don't believe me. Now, the only way we're going to get this t out of the exponent is to take the log of both sides. So if I take the log of both sides, I'm going to go, okay, log of 100 is equal to t over 3 log of 2. How am I doing? Now, log of 100 is 2. How do I know that? I could use a calculator, but I already know this is an answer of 2. Yeah, 10 squared. It's got to be. So, and you can use, if you don't believe me, go, what's log of 100? It should be 2 is equal to t over 3 log 2. And if I have to solve for t, let's multiply by the 3 and get 6, right? I'm running out of room, but that's okay. I'll slide over here, graph this one over here. So I've got 6 equals log of base 2 times t, and I'll just divide, right? So t is going to equal, I'll divide by log 2. So my calculator, can you see that? Am I going too fast? Am I okay? Am I alright? 6 divided by log of 2, and I get an answer of about 19.93, and that's in terms of hours, right? Yeah. So I get about 19.9, and that's in terms of hours. Okay? Now to sketch a graph, we have enough information to do it. So let me go ahead and slide. I'm going to do my graph over here. Okay. We know the initial population is 1,000. So if I just put a 1,000 right here. It's going to be a really easy graph. We don't have to get too complicated, okay? And we know that that's at time is 0. We know also that at 15 hours we're at 32, right? At 19.9 we're going to be at a height of, let's see, 100,000. So let's go ahead and see what we've got. Here we've got, we know that when t equals 5, we've got a population of 32,000, right? When t equals 19.9, we got a population of 100,000. So if this is 1,000, I got to go way up here, right? So let's just go and make these scales so it gets all the way. Here's 1,000, but let's just go, oh man, maybe 10,000, 20, 30,000, right? And I'll never get 100,000. It's too high up here, right? I've got 0. Let's do our 5, and then 15, 10, 15, right? I know that it's going to look, here's my 32,000, it's going to look exponential, okay? It's got to grow exponentially, okay? It's not a perfect graph, but it gives a basic idea of an exponential growth. Now, I could go and put in the back part here too, because we know if we started with 1,000 bacteria, there had to be bacteria before that. So we can go back in time. This is time. We can go back in time because if there was 1,000 to start with, there had to have been more before that grew. Okay, right. So the main thing I did on this graph is I just needed the curve. Okay, it's a pretty steep curve, isn't it? When you're doubling this population, because first of all, we went from 1,000. 5 hours later, we're at 32,000. It's growing exponentially. And then 19 hours, almost 20 hours later, we're at 100,000, okay? All right. That's exponential growth. Let's move on to example 2. Plutonium. Okay, now plutonium, 210 has a half-life of 140 days, okay? So what we want to do is a scientist starts with 300 grams, and we want to find m of t. Now you guys can cross off. We're not going to use base E, so cross that out, okay? We're not going to use base E. It's just much easier to use a 1/2. So here's my formula, okay? I've got my half-life formula in my notes. It's got to be that one right there, right? Half-life. So let's start off with m of t, mass over time, beginning mass, 1/2 to the t over n, okay? Here's my beginning mass, right? That's going to be my 300. Half-life, total time, and n is my cycle, or my half-life. That's my 140, okay? So we'll go m of t equals m0, 1/2 times t over 140. How am I doing? So interesting thing about plutonium, yeah, this is stuff we make the atom bombs out of.
That's polonium.
Oh, thank you. That's polonium. I am wrong. Let me keep going. I'm even recorded by saying that. Yeah, you're right. Okay. Yeah. Let's put 300. So we're going to put 300 here. I got carried away.
We're going to make a compilation of Mr. Davis.
There's going to be a lot of it. Okay, so we've got that. So my equation has got to be m of t is equal to 300, right? 1/2 to the t over 140. Okay, there's my equation in terms of t. Okay, C, find the mass remaining after 1 year. Well, that's 365 days, right? So we're just going to go m of t. It's going to be 300 times 1/2 to the 365 over 140, okay? And I'm just going to use my calculator to do the work. It's pretty easy. Can you see it? There you can. So I'm just going to go clear. We'll go 300 times 1/2, 0.5, right? To the power of parentheses. I need the parentheses because I got to go 365 divided by 140. Okay, close parentheses. Have to have the parentheses here because I need that entire fraction to be in the exponent, right? So what do I get? About 49, okay? So after a whole year, there's going to be only 49 grams of this polonium left. Pretty easy. Not too bad. You just have to use the right formula. Okay, now it's D. We're going to take a little bit more work on D because we're going to have to take a log, but I'll show you why. So now, we want to know the time. So we want to find the time T for it to decay to 200. So we set it equal to 200. Now we're going to go my 300 times 1/2 to the T over 140. And we're going to have to solve for T. Alright, so to solve for T, first of all, let's just get rid of the 300, right? Divide by 300. Divide by 300. So we'll have, if I divide by 300, I've really got 2/3 equals a 1/2 to the T over 140. But if I need to get this exponent down, I got to take the log of it, right? So I'm just going to use a regular log. I'm not going to use an E or anything. So I'll just take the log. I'll scoot it over here. I'll go the log of 2/3. Then is going to equal my T over 140 log of 1/2. Okay. If I multiply by 140, okay, bring the 140 up, I'll have a 140 log of 2/3, and then I'll divide by my log of 1/2, okay, and that's going to be T. Now, of course, I'm going to need to put that in my calculator. It's kind of a mess, but I multiply by 140, right, and divided by the log of 1/2. Everybody see that? Brought up the 140, divide by log of 1/2. Now I'm just going to use my calculator to get an answer. Let's see here. Put it so I can see it on the overhead. So we're just going to go 140, and I'm going to go log of 2/3, close the parentheses, divided by log of 0.5, and I get an answer of about 81.9. Okay, that's the time it's going to take for it to reduce from 300 to 200, about 81.9 days. 81.9 days. Okay, there you go. Not too bad. These are pretty easy formulas, right? And if you've had enough science, you guys know how this works. Okay, ready to turn the page? I'll wait for you. 1 second. No problem. Okay. Okay, so turn the page. Okay. All right, example 3. So a cup of coffee has a temperature of 200 degrees and is placed in a room 70 degrees. After 10 minutes, the coffee is 150 degrees. Okay, so first of all, we're probably going to use Newton's law of cooling. Okay, we're going to use that one right there. So let me write that up here. I'm going to use my T of S equals TS plus D0 e to the negative KT. All right. So let's see what we can put in. First of all, this T of S has got to be my room temperature. So I'm going to put 70 there. So I'm going to go ahead and put 70 plus. Now the D0 is the difference. It's the difference between the coffee temperature and the room temperature. Okay, it's a difference. It's the difference between the coffee temperature and the room temperature. Okay, because so it's going to be 130. Yes, so it's just going to be, so D0 is just simply going to be the 200 minus the 70. Okay, which is 130. Okay, 130, and then I'm going to put in my e to the negative KT. Now we don't know K. And K has to do, it's a constant, it's a number that some very smart scientists came up with, but it depends on the container, right? I mean, if it's a plastic cup, it's going to cool pretty quickly compared to a nice insulated cup, right? So these values are actually figured out by doing some math. So let's do some math and figure out what the K is, all right, in this particular, because we don't know what the container was. So in this case, we've got our T of S equals this, but we need to find K, all right? So to find K, let's look at, there's some more information. We know that after 10 minutes, the coffee should be 150 degrees, okay? So I should be able to put in 10 for T and 150 for the temperature over time, and I should be able to solve for k. So let's do that. Let's go ahead and put in my 150 equals my 70 plus 130 e to the negative k times 10. So after 10 minutes, I'll have a temperature of 150, okay? So it's cooled itself down that much, okay? After 10 minutes. So now we can solve for k, but it might take a little bit of math. We're going to have to subtract, and we're going to eventually have to take a natural log, okay? So first of all, let's go ahead and subtract. So if I go minus 70 from 150, I'm going to get, what do I got? 80, thank you. 80 equals 130 e to the negative k times 10, right? Divide by 130, so I get 8/13, right? Equals e to the negative 10k. I just rewrote it that way. Now, let's take the natural log of both sides so we can get the exponent down. We need to float that exponent down. So the only way to do that is take the natural log. So I'm going to go, I'll have to work over here. ln of 8/13 is going to equal my negative 10 ln of e, right? Negative n 10k ln of e. Of course, ln of e is just 1, so that just kind of disappears. So I'm divided by negative 10, so I get ln of 8/13 is equal to, divided by negative 10 is equal to k, all right? So I'm going to use my calculator, figure out what that value is. All right, so clear that. Can you see my calculator there? There you go. And I'll move my calculator in a second. So I'm going to go ln 8/13, right? Divided by negative 10, and I get a decimal. So k is going to equal about a 0.04855. So with these numbers, try and keep as much accuracy as you can. I'm going to say it again. With these numbers, don't round. Round as little as you can because you're taking something to an exponential power, right? When you take things to an exponential power, every little variation in that decimal can change it radically, right? So we want to keep as many decimals as we think is feasible, okay? Now, I finally have k, which means I can finally make my formula, okay, for this cup. So what we found out is a variable for the type of cup we have, all right? The smaller this number, the more insulated the cup is. Does that make sense? The bigger this number, the less insulated the cup is. Like if it's a Dixie cup, it's going to be a much bigger number, right? It's a nice, good insulated cup. This number is going to be small. Okay, so here's my formula. I'm going to have a T of S for this one. It's going to be my 70 plus 130, darn it, might run out of room, e to the negative, I'm running out of room, 0, darn it, hate when I run out of room. Let's see, where can I put it? Oh, I'll slide it up here. How's that? T of S. Cornell notes are great except for they get too small, huh? 70 plus 130 e to the negative 0.04855 t. All right, we've got a formula for this coffee cup, all right? Now, B, which I've written all over B, but that's okay, we'll figure it out. Find the temperature after 15 minutes, okay? So we'll do B. I'm going to do B up here, okay? We're just going to plug 15 in, right? You okay? Am I being too sloppy? Are you okay with what I'm doing? Mm-hmm. Okay, I'll do B up here. And I'm going to go, okay, well, temperature after 15 minutes, so I'm going to go T of 15 is equal to my 70 plus 130 e to the negative 0.04855 times my 15. Okay, now the cool part is I still have that number in my calculator, right? So when I type it in, I'm going to use my answer button for super accuracy. You want to see super accuracy? I'm going to go and do my 70 plus 130. I'm going to use my E button, and I'm going to use to the negative answer times 15. Okay, check it out. So if by using the answer button, I've got this entire decimal. Talk about accuracy. That's pretty good accuracy, right? So I went the 70 plus e to the, and this is my 0.04855, but by using the answer button, I get much more accuracy. So then I hit it about 132.7. So it's going to be 132.7. 132.7 degrees. So it's cooled down. It started at 200 degrees. It's gone down to 132 degrees. It's cooling down. Okay, now, how long will it take the coffee to cool to 100 degrees? We're not to 100 degrees yet, but we're thinking, boy, I'm not drinking my coffee until it's 100 degrees because otherwise it's going to burn my lips, right? So how long is that going to take? So let's set it equal to 100. So go 100 equals this 70 plus my 130 e to the negative 0.0454855t, and we just need to solve for t. Alright, we're probably going to have to take a log, right? Probably going to have to take a natural log to get this out of the exponent. But let's first subtract from 70. So I subtract 70 and I get 30. Negative 0.04855t. Alright, let's divide. So I'm going to get 3/13. So I'm going to get 3/13 equals e to the negative 0.04855t, right? Natural log of both sides. So I'll do an ln. I'll do an ln of 3/13 equals negative 0.04855t. ln of e, but ln of e is just 1, right? So I can get rid of that. ln of e is just 1. And now what I'm going to do is just divide. So I'm going to divide by my negative 0.04855. Put it into my calculator. Can you see that? Yeah, you can. So we're just going to go ln of 3/13, right? Divided by negative 0.04855, and I get an answer of about 30.2 minutes. Okay, so I get about 30.2 minutes. Okay. Now, to draw a graph, again, all we have to have is the general shape. So I do know this. It is going down exponentially, right? So it's going to have this shape, right? So if it's going to have that shape, let's go ahead and just do our best to just draw a rough scale of what we got. Let's draw here and here. Our beginning amount here's time is 0, right? And I know at 0, I'm going to have some information. I have some information here. This is 30 minutes and it was 100 degrees. I have some information way up here that I've got after 10 minutes 150 degrees, right? So I'll put time down here. And let's go 10, 20, we'll go 30, right? We know it started way up at 200 degrees, 100, right? So it initially started at 200 degrees. So I'm going to put a point up there. So I'll do it in orange, okay? So that's my initial temperature. 200 degrees is when we pulled it out of the microwave, right? Boom. We know 10 minutes later, it was at 150, so I can put a point about there, right? I know at 30.2 minutes is at 100 degrees, about there. Now, it looks like you could draw a straight line, but it's not. We know it's got to go, and it's got to curve down, right? Now, I did not. This one's different. Actually, there's a little bit of a thing there. It shouldn't be, okay? So, let's take a look at this. I really should use my whiteout because, check this out. I kind of made a little mistake, but I didn't do it on purpose. But there really shouldn't be anything right there. This one's different because we pulled it out of the microwave, right? And the moment we pulled it out of the microwave, it was 200 degrees, right? It hit its peak. So it was heating up in the microwave, so we won't show the other part because it was heating up in the microwave. We pull it out of the microwave and then it starts to cool. So we're only going to have that part, okay? All right. Here is homework for today or classwork, whatever you want to call it.